Hello, ladies and gentlemen, everyone. This is Dr. Burns. Welcome back to lecture for the week 5. This is lecture 5B, which is the second lecture for the fifth week of our course. And I'm really excited about this topic. We are finally going to go over caching and what that means and how we can kind of implement some of those things here that we discussed. All right. So here's kind of a roadmap of where we're going to go. We'll go over some of the cache basics. What is it? Why do we use it? Then we'll talk about the level 1, 2, and 3 cache and what they mean respectively. And then also we're going to look at memory hierarchy and then associativity. All right, so let's go ahead and get started. So imagine this, right? For those of us that are shoe lovers, or you can pick really any item that you love. What do you see from this picture? If I were to look for a very particular pair of shoes that I really loved, what do you think would happen? Well, more than likely, it would take some time to find it. Even if I had a system to index them, I still would have to go look through that system and then search through all these shoes to find it, right? Because there's so many items and there's so many variations, it makes it a little bit more time consuming to find it. And it takes a long time, and depending on the shoe, it might be hard to find. Like, what if it's all the way in the back row somewhere, right? And this is some problem that we might have. Now, if you look here, you'll see that this one has a lot fewer shoes, and this is something that I would implement, right? So I have shoes in my bedroom that are kind of on the door, and there's a bunch of them. There's like a bunch of shoes there, and then downstairs um where we kind of go in and out, those shoes are, there's only a few there, and those are the ones that I commonly wear. So the sneakers that I always wear, or particular dress shoes that I might wear that are more common. And the reason I do that is because I can access them really quickly. And if I know there are only pairs of shoes to wear, it's easy for me to choose from that. It takes less time for me to access it, and I'll always have the favorite items that I want available and I know where they are, as opposed to trying to search in this big room full of shoes. Well, cache essentially does the same thing. Caching or having cache memory allows us to access information by having a smaller subset of data. So because this helps us decrease the amount of time that it would take us to search for an item, it ends up helping us to be more efficient in terms of computing, right? Because keep in mind, as we said before, half of the actions that we're doing, or more than them, involve some sort of memory access, right? Whether it's accessing memory for instructions or commands or data, or whatever the case may be, files, right? All of these are going to be us pulling information in and out of memory, right? So if you have this huge area of memory that you're always looking at, it could take a while to search for that. But if you have a subset, it makes it a lot easier. So cache memory is just a small size type of volatile computer memory, right? It's just a small subset in memory that you use for your computer. Now, what it's going to store typically would be those frequently accessed data items, so that you can retrieve it quickly, right? Similar to what we see in websites, right? When it has your cache and it says, hey, clear your cache and your cookies, those cache pages are going to be the things you access a lot, access often, so that next time you pull it up, it doesn't take as long for you to pull up that website. Same thing with memory, when we're accessing information from our regular memory. Now, what you'll see is that the way that this is lined up, it is lined up like a buffer between the CPU and the main memory. So when we look at this, one, the benefit is that it's going to allow us to access the data more quickly. Two, it's going to help speed up your execution time, right? Because the faster that I can get information out of the memory, the faster I can go to my next process. And also, it's going to decrease performance gaps, right? So at the beginning of the class, remember we talked about um, a few things that we want to enhance in our memory, right? We talked about power, your memory, and then also your speed, right? How can I increase that, or performance or efficiency, right? The less time you spend in memory, the more time you can spend doing other items, right? So having an effective cache strategy helps you have a better computer. Now, as we look at its kind of this, its importance or its relevance in computer architecture, we want to consider a couple things. Because it's between the CPU and the main memory. Now, keep in mind that when we look at our computer, if we look at it from a programming perspective, so let me go ahead and put my annotations here. All right, if we had this as a diagram of our computer, this is what the user sees. So this is our GUI, right? They're inputting information here. You're getting the data here. At the bottom, kind of maybe the CPU that is communicating data, is communicating information. And at some point, it's going to have to access this huge RAM of memory, right? So as I'm accessing this memory, I'm going back and forth, and I'm going to put this cache right in between here in order to be able to go from here. I can go back to this a lot easier. If I don't find it there, then I can go back to my main memory. So that's kind of where it is, and we'll see a better, we'll actually see a much better diagram later on in the class. When it talks about the this gap between the main memory and the CPU, because the main memory is so large, and the CPU is so vital, there can be what we call a performance gap if it has to search through this massive amount of data. So when it says it bridges this gap, it's talking about kind of the performance gap that it would take if you were searching the full amount of your main memory. It's going to enhance the computer performance and increase efficiency. I think I said that already. It's kind of redundant. All right, so let's look at the hierarchy, right? We have our processor or our CPU and our memory. What I was trying to draw before was that in between that, we have this cache, which serves as a sort of ally between these two or an ambassador between these two to help facilitate quicker communication, right? If I have 1,000 shoes here, right, maybe I'll just put the six right here and I can locate those six pairs of shoes and give it to the memory quickly. Then the memory doesn't have to bother the processor and it can just handle business. Sort of like managers, right? A lot of people have this structure where they have senior managers and then they have other managers, right? So you might have a senior manager that manages three people, and then those three people are middle managers that then manage the other parts of the company. So now I don't have to talk to, the senior manager doesn't have to manage 35 people that can be distributed to other ones with a smaller amount, which allows them to more quickly and efficiently access and handle those situations. Now, when we look at data flow, right, we have the processor kind of talking and communicating back and forth between the memory. And this cache goes pretty much in between that. It can talk between both of them, right? Do I have this item here? Cool. Let me then give it to memory. Do I not have it here? And that's when we start getting into hits and misses. We'll talk a little bit about that in the next lecture. But if I have access data from the cache, then I don't need to go to main memory. If it's not in main memory, which will be known as a miss, then what you're going to do is, I'm sorry, if it's not in the cache, then that will be known as a cache miss. Then you would go ahead and find that from main memory and then store it in the cache, right? So that's where this thing comes here. And this we want to kind of avoid because we don't always want to have this processor talking directly to the memory just because it takes a massive amount of time. All right. So let's look at this conceptually. Again, this is from the Carnegie Mellon site, and their classes and their concepts in terms of this. Let's say we have these addresses for our data that we're trying to access. Now notice I'm going to say that my processor is going to be right here. My processor says, hey, I want to get data from here, right? If this main memory, if this was not here, my processor would have to search. It wants to get at the address 10. It would have to search through all these 1, 2, 3, 4, 5. It would have to search through 10 different addresses just to access this guy, right? So now I'm going through 10 operations just to get to this thing right here. But when I add this cache, I only need to go through one operation, or really these two other memory blocks, in order to access it, which is going to save me. I'm basically spending less than half the amount of time in order to get to that. So, right, we can see automatically how we end up saving time there. Now, when we talk about our memory, a lot of times it's like the RAM memory. It's going to be larger, um, allowing you to store more data, but it's also going to be slower. Your RAM memory is going to be cheaper than what you might use for your cache, but it's going to be slower. So you kind of have this cost trade-off as well. So you want to consider that, especially when you're designing a computer, right? How much cache do I really want, right? Because price is going to be an important factor. So, hey, yeah, I could put a bunch of caches in here, right? But then your computer's going to be really expensive. And there becomes a point where if you put too much cache, or you make your cache too large, then it will end up with the same problem that you had with your main memory. We're searching these large banks in order to find the data. All right, so talked about that. Now, there's different levels of cache, right? And what does that mean? That means, let's go back to this diagram. Let's say, oh, I erased my processor. I should have done that. All right, that's fine. I'm gonna do it this way. So I have my processor here. This is gonna be our processor. The one way I can access it is through this one, right? Let's say I go through this level. Let's say now the address that I'm looking for is 14. I go through this first one, right? If this is my L1, we'll call this L1. The information I'm looking for, let's say I'm looking for this data now. I go through L1, I don't find it. I can make another cache right here, which I could call L2, and then I could store that data here, right? So if I did another cache on top of that, what would happen is first I would go to L1. All right, now keep in mind this is our processor. All right, I go to L1. It's not there. Okay, I can go to L2. And let's say L2 has this in its first memory bank. Boom, now I found it. I can go back up here. If I try to do that and go back down to the memory, I'm still going to have all of this data that I then have to send through. But if I make another cache next to it, I can still save some time in terms of my search mechanism. So when we talk about these layer 1, layer 2 caches, typically what you'll see is that it'll expand. We'll go to the first layer first. If it's not there, we might go to the second layer. And then if it's not there, we're going to go to that third layer, or for the cache. With each time, it ends up getting a little bit larger in size, but it still saves us a little bit of time if we don't need to go and search the full memory. Okay, so this is layer 1. If it doesn't tell you and you just have a one cache scheme, then it's always just going to be layer 1. All right, so each layer cache is going to have things that it's better at, or things that it's known for, right? So the L1 cache is what we call the lightning fast cache, right? That's going to be your quickest one. It will generally be your smallest cache, and it will be the one that you can access the most rapidly and get your information from really quickly. When we go to L2, that is what we're going to call the bridge, and we'll talk about that, why it's the bridge, a little bit later on. And then your L3 cache is going to be your shared resource that you use to gain and access information from various platforms or various applications, right? So we have all of these, and over time, they've kind of had developed different functionalities, but they all kind of aid in improving the system performance overall. All right, so this kind of shows a little bit of the from this site here, tech4gamers.com. because this is going to be really, really important as a gamer as well. All right, so you can imagine this, right? This is kind of your how you're looking at when you're in these caches, right? Just like I said before, I have my processor that's trying to get information here, and at the bottom of this is this big, large, huge bank for my local memory, right? I don't want to have this searching this huge bank. So what I have here is my processor is looking at what I call my the registers, right? We've become very familiar with that even as we look at the assembly code information. And we have something that allows us to look at this L1 cache, all right? If it's not there, then the next thing we're going to go to is the L2 cache. And then finally, if we don't find it there, we go to the L3 cache, which is our shared variable. And then this is after we can't get all that, then we're just going to go ahead and go to our local memory. Keep in mind, this is speed. This is going to kind of be this bridge. And this L3 is going to be a shared resource, right? Because the L3 cache can be accessed by various components of your computer in order to share information. Um, and then that's going to be the last one right before we get to the main memory. All right, so let's look at this kind of lightning fast access and see where we are, right? Um, this is our layer one cache, the first one we get there. Um, it's gonna typically be very small in size, and it's gonna allow you to store data for like your frequently used instructions. So if I'm constantly saying, hey, I want to add this, or multiply this, and I know I have a certain data set that I'm accessing over and over and over, then I want to store it in this cache right here. I don't want to put it all the way down in main memory. And as you can see, so sorry. As we can see in that diagram from before, you can access that via the CPU. Now, for the L1 cache, let's go ahead and look at the performance implications. It's going to increase your CPU speed. It's vital to your performance. So the L1 cache is like the most important cache that you'll have in terms of improving your performance. You want to make sure that's working well and effectively. The other ones are going to be they're going to be below what you see here. And as we stated before, this is just going to allow you to quickly get data. Also, quick access to instructions and executions. Now, when we think about this, what will we use it for? The L1 cache is commonly used for like game instructions in video games, right? Because I want to be able to quickly, if I'm playing a game, I don't want to wait, right? And already know what memory address I'm going to be accessing for these games, right? Because a lot of them are the same commands. It's going to be operating in the same memory space. So I want to use the L1 cache for that because I want to have that speed. I want to make sure I can get in, do my all my moves very quickly, and then be done. When we think about the L2 cache, this is what we want to call the bridge. And this is because it's positioned between the level one cache and the RAM, right? So provided that you actually do have an L2 cache and it's not just a single cache system, this is going to be go right in between those two. And what it does is it allows you to gain more, it gives you more space to store those frequently used instructions. So one might ask, why would I want a level two cache? Why don't I just store all of the instructions in level one? Well, or layer one. Um, layer one, level one, whatever the case may be. You don't want to do that in an L1 cache because if you make that larger and larger and larger, then you're going to have the same problem that you do with main memory, and that it's going to take you too long to access your instructions. So having it separated by layers or levels allows you still to have a little bit more speed. Once you get down to this layer two, you can store even more data there, even more instructions for relatively quick access. Now, in some computer systems, you will have the level 2 cache or layer 2 cache um, accessed by different CPU cores. So it can share information among those core values. Not all of them will do it, but some of them will. Now, when we talk about performance implications, how does this help our computer? It helps us by storing that data that we don't have in the level 1 cache. Um, it's still going to reduce the CPU memory, CPU to main memory access. Now, keep in mind that layer 1 or the L1 cache, what that did was it really increased our performance overall. Now, for this one, it's going to be an addition to that and really help you kind of decrease the time that it would take you to get to that main memory. And it will, of course, improve your system performance. So the question might be, where are we going to use this, right? Who cares about that? We have the layer 1 cache. We might use it for gaming instructions because I'm like, I quickly want to be able to get these commands out. We're thinking about the L2 cache, right? This is more for this bridge of getting information and data. We'll see that as an example when you have picture data for editing software. Now, keep in mind, if you have editing software, there's just going to be a massive amount of information for pictures, and you don't want to keep that in your L1 cache, right? You want to keep your L1 for common instructions and common data. But as you go to like pictures and you're editing things, you have probably too much information or too much data to store that all in the L1 cache. Now let's go into the layer 3 cache. Sharing is caring. So for your layer 3 cache, your L3 ones are going to be accessed by the CPU cores, right? Sometimes it will be layer 2, but layer 3 will generally be accessed by multiple CPU cores, allowing you to kind of share data and get information across different processes. It's a good common space for data instructions that are going to be common among a lot of processes, like, get, retrieve, store this information here, whatever the case may be. So this will be really good for making sure that you have access to those items. And of course, it's going to improve your CPU efficiency. Now, as we deal with these multi-core processors, right, having an effective level 2, level 3 cache is going to be really important, right? The better those cores are with retrieving information, unless they have to pour from main memory, the quicker they'll be able to handle the processes that you desire, right? So you want that to be effective as you're dealing with multi-core processing information. Now it is going to, of course, as we said before, give you this good way to share data among cores, and again, it's going to reduce their frequent access to the main memory. So where might me use this L3 cache, right? What is it going to be for? One example would be like database tables and indexes, right? If I know I'm handling a process that's going to go across multiple cores, I'm accessing a database, we can store this right in the L3. That means multiple cores can then access that. So let's look at this not just in terms of the basics, but let's do a kind of comparative evaluation of these. RAM, your RAM memory, this is going to be your main memory. It's going to be your largest size. Actually, I'm sorry. Let's go from L1 on back. So in terms of your access speed, as I stated before, L1 is going to be the quickest. Um, this right here is going to be your typical size of it, right? 16 kilobytes to 128. And again, you could go a little bit larger, but you want to be careful because the larger you go, it kind of defeats the purpose. The cost of this is going to be the most expensive for those items. When you get to L2, you'll see how the speed decreases, 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 and so does the cost. Right? This faster it is, and more expensive it's going to be. And you'll see how the size is going to increase as we go up and up through these various memory types, right? Until we get to the RAM, which is going to be the slowest of all of the memories. And not only is it going to be the slowest, but it's going to be the largest, and it's going to be the most cost effective of those three of the four memory types. All right, so let's look at it in terms of the memory hierarchy and how all of these goes. If we consider the L0 as kind of where the registers are holding information, you might consider these as your different levels of cache. Now, you can add as many layers as you want. So if you had something that was 6 layers, this would be a good way to kind of recognize or represent kind of where they are, right? This top of this pyramid means it's going to be faster, but it's going to cost more money. Then we get to the bottom of it, and it's going to be cheaper per byte. And what you guys want to look at is kind of let's consider um the applications and the functions of each of these. As we look at this, your L1 is going to keep your cache lines and information, and it's going to have this communication kind of between the L1 and the L2 information in those cache lines. When we get down here to this DDR or this main memory, your main memory is going to hold your block of information and things that are retrieved from the local disk. So we can kind of see how these are all access and where these are in terms of the different things, right? Well, L1, 2, and 3 being those cache registers, and then here your main memory, and these disks or these informations here are your local disks and secondary storage that are being used for other operations. Okay. So we start off with the main memory and an address we're looking at, right? And then we take that address and we put it in a subset, right? So as I put it in this subset, now I need a way to reference it from that subset or a way to determine how I want to enter it into the system, right? The same if we go back to the example of the shoes. Um, when I'm looking at my shoes, which one do I want to put on the top row? Which one do I want to put on the middle row and the bottom one? Typically, I'm going to put my most often shoes, the most often used shoes, somewhere where I'm going to access them frequently. So I might put my most often ones in that middle row because I can just grab it. And then I'll put the second one at the top one because I can grab it next. And the ones that I use least often, right, they're going to be on the bottom and they're going to require a little bit more effort for me to get them. When we look at memory, we have to determine our theme and mechanism for how we want to map that to cache. Now, that's going to be different depending on your cache. Like for me, for my shoes, I don't want to put the common one at the top because I'm short. So if I'm trying to always reach up to access those shoes, it's not beneficial. So I will put mines in the middle, right? But somebody else might be like, my husband's 6 feet tall, so he's gonna put his at the top, right? Just like there's different ways that we would store information for things that we want to access commonly, there's different ways to store your memory types in a cache, right? So we're going to talk a little bit about that. We're going to talk about what that means to map it so that you can easily access and how you want to store the data in there overall. So, when we think about this, as we're talking about mapping, right? Mapping just gives you a way to identify how your data is being stored in your cache, right? If my memory address is 0x4ECC123, right? I don't necessarily want to have all of that information when I'm trying to look for it. So I will generally have some sort of mapping that makes it easier to find. Tag, so the data is the information to be accessed. Your tag is the memory location. That means what is the address, right? The address of where that was originally in memory. Then we have the line or the block. All right, so There are different nomenclatures. Some classes say lines, some classes say blocks, some examples say lines, some examples say blocks. But this refers to the storage unit that contains multiple bytes of data. So that means that if I have something, let's say it's 8 bytes, right? This I'm actually the example that we did last time, we said typically when we look at something, for example, in a memory or a data type, we typically put those in 4 block increments, right? So that line or block will be that collection of bytes that we use to represent a block of information. A set is a collection of blocks, right? So your block is just one unit of data, right? And then your set is a collection of multiple of those units. Okay, so those are the common terms. Now you'll see that kind of referred to here as we talk about associativity. Associativity is basically how we describe how we're going to map out items in our cache. And there's gonna be 3 types of associativities um, that we discuss it in this class. One is direct mapped. That means that every address is mapped to exactly one location in your cache. We have your fully associative cache, and that means that you can map that um, address to any location. It will accept any location. I can map it wherever I want. And then we have the set associative. Now, your set associative is the most commonly used one. And that's where you map to a specific number of locations, right? Meaning I have different places. I have a specified number of sets that I can use for this memory address, and that's where I'm going to map it. Now, this will make a little bit more sense kind of as we continue with this example. Let's say I am searching for a cache, right? Or searching through a cache. When I have my direct map here, tag, right? This is your memory address, right? This is telling you the memory address this is looking for. This I'm using a search mechanism to search for particular information. This is my block, right? This block is just going to be a collection of data. This is going to be a unit, right? This is 1, 2, 3, so 8, essentially 8 blocks is a unit. And then here's my data. If I want to search for 5, I now know 5 is right here. And what happens is these 7 spots are always going to be mapped to these 7 addresses in my memory, meaning that my memory is always going to be mapped to these 7 spots in my cache. It's not going to change. I can't put my 5 over here. I can't put my 1 down here or map it differently based on my feeling. If it's 5, it's going to be 5. It's always going to be in that same location. And for this, as you are searching through this, when I'm trying to determine how to gain and get information or access information from that, I can only search one block at a time. So I'll go through this one, this one, this one, this one, this one, until I get to my item of interest. When we look at set associative, I want you guys to notice a couple things here. For our set associative cache, these are broken into sets, right? I still have 8, we'll call it 8 bytes of information, right? But notice how the blocks are now broken up into sets. This is my first set. Looks like each of these contain one set contains 2 blocks. This is my second set. Right? This is my third set, and this is my fourth, so on and so on. And as I'm looking at that, for this one, you can search one set at a time. So if we go back to the original one, we'll see that for our direct map, ooh, that's the wrong one. For our direct map, we are only searching one block at a time. For this, it's one set at a time, which means I can search both of these blocks within that set. I can then search both of these blocks within that set. So I'm searching each individual set at one given time. For fully associative, let's get this out of here. Fully associative, so this light orange indicates that everything is accessible, right? There's no, I can only search this. It's going to search all lines in parallel. And that's kind of what this orange means. So if I'm at direct, I'm only looking at one line. If I have set associative, I'm looking at the number of sets that it has. So in this particular one, I'm looking at two lines at the same time, the next two, the other two. For a fully associative, I'm looking at all 8 lines all in parallel. And that's how we kind of deal with and handle that search mechanism. So then the second question is, okay, this is how we read from the cache or how we search through it. What happens when we uh, are trying to write to the cache, right? That's where we can really see kind of what's happening here. For a direct map, so let's look at this example and kind of what this is telling us here. It says you have a direct map, there's 1 line per set, and your cache block is 8 bytes, right? Your block, remember this is one cache block, right? 0, 1, 2, 3, 4, 5, 6, 7, or 8, it's going to be 8 bytes here, right? We'll go over this a little bit later on. This is kind of like your validation bit. Here's your tag. Your tag tells you where is located in the cache, and then here is your memory address, right? So that's kind of how that's broken down here. If I were to wanted to find that, this memory address would typically be built on the same location for my direct memory, my direct map. So let's look at an example for this. Let's say we have this program here, right? Very, easy, common program here, where I'm looking at this data and I have 5 variables, X, Y, Z. Sorry, I do not have 5 variables. I have 4 variables. Hmm. What is supposed to be 5 variables? I have 4 variables, and those variables are X, Y, Z, and A. I am not sure why I declare this as X again, but here we are. All right. So let's say I have that information and I want to update this or include this kind of in this storage loop here. I have a for loop that then has this variable I that I'm going to go in. I'm going to take X and I'm basically going to add 1 to it. Each time I go through this for loop, I'm going to go through it 4 times. And then I'm going to multiply uh 2 times X to get my value for Y. I want to compare that to Z. And then if Y is greater, then I'm going to go ahead and set that to 1. And then I have these where it just combines all of these data points and then adds them together. So I'm clearly accessing these variables often, right? If I look at my X, I access my X 1, 2, 3, 4, 5, 6, 7 times, right? So I want to have that stored somewhere where I can easily get to it. So in a direct map, if I know what the memory address is, I'm going to say X is equal to 1, and I'm going to go ahead and store that right here. This is a one-to-one map. This first item is stored here. That's where it's going to stay, and that's where we're going to keep it. When I go to y is equal to 0, similar thing, where now I'm going to store my y into that next or that adjacent item in memory. And then z, right? If I happen to, for some reason, store z in this memory block 1, this is where I will put it in as far as the set as far as the this direct memory flow. And then finally we have A, which is our last item, and we would store that in the empty spot for that. All right. Now, let's look at another example where we have something called a set associative cache. Set associative, if you had something that says, hey, there are 2 lines per set. So let me show you what this means. We'll step back a little bit. Notice how, so these are our lines, right? This is when I'm dealing with a direct map. And it tells you about the block size and all that. Now, when I go to here, notice how it tells me that I have the block size. Sorry. The block size is still 2 bytes. I'm sorry. The block size is still 8 bytes. But notice how now I have 2 sets. Or it's telling me that I have 2 lines per set. So I can search both of these at once. Before I had just 1 line, but now I can go ahead and search both of these lines each time I go through this particular item. All right. Now, notice the difference in how that is portrayed here, right? Remember from the direct map one, I say, hey, x is equal to 1. I have that data here. This is where it's stored in memory. For my set associative, notice how I'm somewhere down here in memory, but where I want to store it, right, when I'm writing to the cache, I'm just going to write it to this first set here. And notice how already I'm going to store this in one aspect right here, right? This is one portion of the set. And then the next portion of the set, I'm going to store y is equal to 0. So I have both of these. They're stored in one set. They happen to be stored in set 0. And that's kind of how it is mapped. Multiple blocks put in the same set. Now, we're going to add another one, z is equal to 4. Z is equal to 4 is going to go right here. Now, typically when you're writing to the cache for set associative, that's typically going to be in sequential order in terms of where the set is. So if you're with direct mapping, it's going to be in the order that is closely related to the actual address. For a set associative, when you write it, you're gonna start by writing at the first item that's free in your cache. So here, 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 here. The next one we go here, here, then here, here. All right. Anyway, z is equal to 4. That's my next item. And then I go a is equal to 0. So I have both of these these items being stored a little bit farther away in memory, but that's fine. And they're placed right here in the set associative cache. As I was mentioning before, it is a sequential write, meaning that it is going to write to the first area in the cache that is empty. All right, so that's where we're going to end the class for today. Um, we'll kind of pick up on this tomorrow, not tomorrow, whenever we go into next lecture. Since we now know how to write to it and we know how to read from the cache, we're going to talk a little bit about replacement policies and then what hits and misses are. All right, guys, enjoy the rest of your day, and until we meet again.